Okay, so first we're going to go over the intuition behind the pumping lemma to get a better idea of why the statements said within the lemma are the way they are. So before we can do that, we need to go over some key concepts. The first concept to remember is that regular languages, so RL, are any language where there exists a DFA that can accept string within the language. So we know that if a language is regular, then there exists a DFA that can accept it. That also means that if a language is not regular, then there is no DFA that can accept it. So it's impossible to make a DFA for a language that isn't regular. Okay, that's the first concept that we need to remember. Another concept we need to know is the pigeonhole principle, which is like a mathematical statement. So pigeonhole principle. Okay, so this principle says that if you have at least n plus 1 pigeons, so n is just some number over here, and you have n pigeonholes, so you have more pigeons than you have pigeonholes, and then if every pigeon flies into a hole, at least one hole will have more than one pigeon inside of it. That's because we had more pigeons than we had holes. So for example, if we had 3 boxes, and then we had more objects than we have boxes, let's just say we have 4 balls, and then we put each of these balls into a box, then what happens is that no matter how we arrange these balls into each box, there will be at least one box that must have more than one ball, right? Because there's more balls in our boxes. So that's what the pigeonhole principle says. Now, how does this relate to DFAs? Well, let's think about the amount of states in a DFA. So we know that the amount of states in a DFA is finite because the F in DFA stands for finite, and that is with respect to the amount of states in it. So we'll say that a DFA has n states. Any DFA will have n states, where n is just some number. Let's think about what happens when a DFA reads in strings of different length. So if a DFA reads in 0 characters, then how many states will we have seen? Well, the answer is 1, just the start state, right? So looking at this DFA, if we read in no characters, so like epsilon, then how many characters will we have seen? I mean, how many states will we have seen? Well, it will be just 1, which is Q0, because that's where we started. So if we read in 0 characters, we see 1 state. If we read in 1 character, then we've seen 2 states, because after reading in a character, we go to another one. After reading in 2 characters, we'll see 3 states. And when I say states, I don't mean unique states. I just mean states in general. And so after reading in n characters, we will have seen n plus 1 states. So for example, let's take a string that this DFA accepts. So this DFA accepts any string that starts with a 1 and ends with a 1. So let's take 101. This thing has 3 characters, and so we expect to have visited 4 states after reading it. So let's see what happens when we read in the string. At the start, we're at state Q0 because we've read nothing. Then we read in 1, we go to Q1. Then we read in 0, we stay at Q1. Then we read in the last one, and we go to queue accept. And so we visited 1, 2, 3, 4 states as expected. So the statement is like obviously true. This one over here. So if you read in n characters, then you will visit n plus 1 states. Okay. Now, let's say this DFA that we're talking about, so any DFA accepts some string w where the length of w is at least n, with n being the same number here, so the amount of states. So it accepts a string that has the same at least length equal to the amount of states. Then, after reading in the string, w, how many states will we have visited? Well, it will be at least n plus 1. Right? So if the length of w was equal to n, so the amount of characters in w were n, then after reading in w, we will have visited n plus 1 states. And so if the length of w is greater than equal to n, then the amount of states we have visited would be greater than equal to n plus 1. Okay, so what does this tell us? Well, by the pigeonhole principle which we mentioned earlier, we will have visited a state we've seen before along the sequence of states we visit. So at least one state will be visited twice. Because we visited more states than there are states in the DFA, right? And so what this means is that we have a loop somewhere in the sequence of states that we visit because we started at one state and we ended in that same state since there's a repetition. So let's apply that to this DFA over here. How many states does it have? It has 4 states. And so what we expect is that if we have a string of length at least 4, then as we read in the string, we see some state more than once. Let's take this string over here, 1001. The length of this is at least 4, and so we expect to see a repetition as we read it. So we start off in Q0, read in a 1, we go to Q1, we read in a 0, we stay in Q1, then we go to Q1 again, and then we read in a 1, we go to Q accept. And so it did happen. We have a repetition of states. So in this sequence of states, we visited 1, and then we visited again. And so there's a repetition. And what that means is that there's a loop in the DFA. And we can see that it is true, in fact. We have a loop over here. And so the thing about loops is that we can traverse them any amount of times, and we'll still end up in sort of the same place after reading the entire string. So let's just think about how that works. We had string 1, 0, 0, 1. The loop happens when we read in this 0, right? Because after this character, we're in Q1, and then after reading 0, we loop back to Q1. And so what the loop being there means is that we can keep following this loop as many times as we want, and we'll still end up in the same endpoint as we would have without the loop. So let's just repeat the part that causes the loop 2 times. So before the string 1001 ended in Q accept. And now we have repeated the looping part of the string 2 times. And so we expect it to still end up in Q accept. Let's see if that's true. So we read in 1, we go to Q1. read in 0, stay in Q1. Then we stay in Q1, stay in Q1, stay in Q1, or we go to Q accept. And so we see it's true. If we have a loop in a DFA, then we can traverse it any amount of times and still end up in the same place after reading the entire string. And so we can take any string that causes a loop, so as before, 1001, and we can break it down into 3 parts. The part before the loop, the part that causes a loop, and the part that is after the loop, okay? And so what we said before is that we can repeat the part that causes a loop any amount of times, and the string will still end up in the same final state. We can also skip the part that causes a loop, and we'll still end up in the same place. And another thing to notice is that by the pigeonhole principle, the repetition of states happens within the first n characters, because if we read in n characters, we visit n plus 1 states. And so the repetition must happen after reading in the first n characters. And so what that tells us is that x and y must have length at most n. So y is the part that causes the loop, and x is the part before the loop. So the part that causes a loop must occur after the first n characters, where n is the amount of states. So altogether, if a DFA has n states, and for every string w that it accepts, where the length of w is at least n, we know that along the path of reading the string, we have a loop. And so we know that we can break it down into 3 parts. W equals to x, y, z, where x is the part before the loop, y is the part that causes the loop, and z is the part after the loop. Right? Okay. So we can break it down to these 3 parts, where the following things are true. Y is non-zero, because y is the part that causes the loop. And it has to be non-zero because of the pigeonhole principle, which says that there basically has to be a loop. So y can't be empty. So that's the first thing. Next is the other thing that we mentioned, that the part leading up to the end of the loop happens within the first n characters. So the length of x and y together is less than or equal to n. And the third property, formalized in mathematics, is that we can either skip the part that causes the loop, or we can repeat it as many times as we want, and we'll still end up in the same state at the end. So in mathematics, we write it like this. X, Y, I, Z is an element of the language of the DFA for I greater than or equal to 0. So this just says that we can either skip the part that causes the loop or repeat it as many times as we want, and the string still ends up in the same place. So if we take a string that is accepted, then we know that after reading in the string, the DFA ends in an accept state. And we said that because of this property, the DFA ends up in the same state no matter how many times we repeat the loop. And so if we have a state that is accepted, which ends in an accept state, then after repeating the loop as many times as we want, we still end up in an accept state. And so the string must still be accepted, which is why the pumping lemma says that. So all together, let's write out the pumping lemma one final time. So for any regular language, so any DFA for which any language for which a DFA exists, there exists some number n called the pumping length, and n has to be greater than equal to 1 because a DFA cannot have 0 states. Remember that n actually represents the number of states in the DFA, and so it has to be greater than equal to 1. So for all regular languages, there exists a pumping length n such that for all strings in the language, so strings w, where the length of w is at least n, we can break it down into 3 parts because we know that this string will cause a loop. So again, x is the thing before the loop, y is the thing that causes the loop, and z is this thing after the loop. So we can break it down to 3 parts such that 3 properties hold. And these are the ones we mentioned before. So y is non-empty because the loop has to exist. The length of xy is at most n because the loop has to happen in the first n characters by the pigeonhole principle. And no matter how many times we repeat or skip the part that causes the loop, the language is still accepted. And so that's the pumping lemma essentially. I hope that made sense, and if it didn't, then just please let me know. I'll explain it again. I remember the pumping lemma says that there exists a breakdown. It doesn't say every breakdown works, but there just has to be one way of breaking it down. So just to reiterate, that means that if we have a string that has at least length 4 for this DFA, so the number of states, and is accepted by it, there has to be just one way of being able to break it down that satisfies the pumping lemma properties. So let's take this string for example. It has at least length 4, the number of states in the DFA, and is accepted by the DFA because it starts and ends with a 1. And so the pumping lemma tells us that there must be a way of breaking it down into 3 parts where the properties hold. Now that doesn't mean that every single way of breaking it down works, there just has to be one. So for instance, if you break the string down into something like this, so y will be this, z will be this, and then x will be epsilon. Sorry, that's not epsilon. Okay, why wouldn't this work? Well, because if you pump down, so if you remove y from the string, then the resulting string will just be 1. And 1 isn't accepted by the DFA. So therefore this is a breakdown that wouldn't work. But that doesn't mean that the string breaks the pumping lemma properties, because there does in fact exist a breakdown that does work. For instance, we could instead break it down in this way. We can let x be this, let y be that, and let z be this. And so this works because even if you remove y or repeat it any number of times, we still end up in the accept state. So this string is pumpable and all the pumping lemma properties hold. So what that means is that if we're trying to prove a language is not regular, and we take a string from that language, and then we try to show that the pumping lemma properties don't hold, we can't just show that it doesn't hold for one breakdown. We have to show that any way that you break down a string leads to an issue. Okay, so that's it for the intuition behind the pumping lemma.